lesson. It's about electronegativity, electropositivity, radicals, oxidation state. Yeah, we are going to look at all those aspects. Alkali metals react by losing the outermost electrons to form a monovalent cation. What does this mean? It means alkali metals lose the outermost electron and the valency of the alkali metals is 1. That is why we say they are monovalent. And it is a positive charge. A positive charge. That's why we are saying a monovalent cation. Now let's see, for example, in the following diagram, we have lithium losing 1 electron to form lithium ion. First ionization energy is 520 kilojoules per mole. Sodium, on the other hand, loses 1 electron to form a positive sodium ion, as shown, and the ionization energy of sodium is 496 kilojoules per mole. The other one is potassium, which loses 1 electron to form a positive charge, and the ionization energy is 419 kilojoules per mole. From this table, we can be able to note that the ionization energies of alkali metals reduce down the group. The ionization energy decreases down the group due to the increase in atomic radius. This increase in atomic radius decreases the attraction between the outermost electron and the positive nucleus. Hence, it becomes easier for the outermost electron to be lost as we move down the group, because the energy levels are many and the outermost electron is held further from the nucleus. Hence, it requires just a little energy to be removed. Hence, potassium, having the largest atomic radius amongst the first 3 alkali metals, requires the least energy to remove the outermost electron. Therefore, it is the most reactive or the most electropositive element among the first 3 group 1 elements. So this potassium is the most reactive among the first group 3 elements. Lithium, sodium, and potassium react vigorously with both air and water, and that is why they are stored under liquid paraffin. I'm sure you've heard of potassium, especially packed in liquid paraffin, stored under liquid paraffin. So the reason is because they are very reactive with both air and water. When sodium is exposed, it reacts with moisture in the air to form sodium hydroxide, which further reacts with carbon 4 oxide in the air to form sodium carbonate. This one is shown in the reactions below, the equations below. In the equation below, we have sodium reacting with water to form sodium hydroxide plus hydrogen, and sodium hydroxide plus carbon 4 oxide to form sodium carbonate dot water. Reaction of alkali metals with air or oxygen. Sodium burns in air with a yellow flame to form a white solid, which is a mixture of sodium oxide and sodium nitride. But sodium oxide is a major component because oxygen is more reactive than nitrogen. The equations for the reactions are as follows. We have sodium plus oxygen to form sodium oxide. Then we have 6 sodium plus nitride to form sodium nitride. So the component of sodium oxide is normally more than the sodium nitride, because we know oxygen is the active part of air. So most reactions will be more in the presence of oxygen than nitride, which is the inactive part of air. But the fact that sodium is a reactive metal, that is what makes it able to react with nitrogen from the air. When water is added to sodium oxide, an alkaline solution is formed, which is sodium hydroxide. So after the sodium has reacted with oxygen, when we add water, then we will form an alkaline solution, which is called sodium hydroxide, and it turns red litmus paper to blue. Sodium oxide plus water is sodium hydroxide. Now when water is added to sodium nitride, ammonia gas is evolved, which has a characteristic pungent smell and turns red litmus blue. So here is the reaction between sodium and nitrogen, whereby it forms sodium nitride. And when water is added to the sodium nitride, then ammonia gas is evolved, which has some smell, some pungent smell, and the solution turns red litmus paper blue. Sodium nitride plus water is sodium hydroxide plus ammonia solution. So that is the equation for that reaction we've just discussed up there. Sodium burns in air enriched with oxygen to form mainly sodium peroxide, which is yellow in color. So here is a situation whereby it is purely oxygen burning the sodium. That is why we are calling it enriched with oxygen. So sodium with pure oxygen, then it will form sodium peroxide when it burns, which is yellow in color. Sodium plus oxygen, enriched oxygen, to form sodium peroxide. That is the equation for the reaction. When water is added to the sodium peroxide, a gas that relights a glowing splint, that is oxygen, is evolved. The equation for the reaction is as follows: sodium peroxide plus water to form sodium hydroxide plus oxygen. Potassium burns in air with a lilac flame to form a white solid, which is potassium oxide. Now a lilac flame is a purple flame. Therefore, potassium will burn with a purple flame, which we refer to lilac flame, to form a white solid, which is sodium oxide. This is according to the equation below. So the equation is potassium plus oxygen to give us 2 potassium oxide. Lithium plus oxygen is lithium oxide. The equation is as shown below. Lithium burns in air with a red flame, forming lithium oxide, and the equation is as shown below. Reactivity of group 1 metals increases down the group due to the increase in atomic radius, which decreases the force of attraction between the nucleus and outermost electrons, and also increases the shielding effect. Hence, the electron is more easily lost in larger atoms. Reaction with water. Alkali metals react with water to form metal hydroxide and hydrogen gas. The reactivity of alkali metals increases down the group due to increase in atomic radii, which increases the ease in which the atom loses the outermost electrons. The table below shows some observations which are made when alkali metals react with water. For example, in the case of lithium, the metal floats on water. Effervescence or bubbles of colorless gas are produced that extinguish a burning splint with a pop sound. The resulting solution returns phenolphthalein indicator into pH 12, 13, 14. That is a base. And the reaction is moderate. In the case of sodium, metal floats on the water, melts into a silvery ball, darts on the surface of water, very rapid effervescence of a colorless gas produced that extinguishes a burning splint with pop sound. Resulting solution turns phenolphthalein indicator into pink, and the pH of solution is 12, 13, 14, still a strong base. And the reaction is very vigorous. Then potassium Metal floats on the water. Metal, it melts into a silvery ball. It bursts into a lilac flame. Darts on the surface of the water, producing bubbles. And the colorless gas produced extinguishes a burning splint with an explosion or a pop sound. The resulting solution turns phenolphthalein indicator into pink. That is a pH of 12, 13, 14. That is a strong alkali. And that reaction is explosive. It explodes into a flame and should be avoided. Now, explanation. Alkali metals are less dense than water. They therefore float on water. The reaction produces hydrogen gas, hence effervescence occurs. The metal melts into a silvery ball because the reaction is exothermic. And hydrogen burns with a pop sound. The hydrogen produced propels the metal, hence darts on the surface of the water. Alkali metals react with water to form a strongly alkaline solution of their hydroxides, and hence turns phenolphthalein indicator into pink, turns red litmus paper to blue. The rate of this reaction increases down the group. That is, potassium is more reactive than sodium, and sodium is more reactive than lithium. The equations for the reactions are as follows. Lithium plus water to form lithium hydroxide plus hydrogen. Sodium plus water to form sodium hydroxide plus hydrogen, while potassium plus water forms potassium hydroxide plus hydrogen. And you can see the reactivity increases down the group because of the reasons we have given above. Potassium bursts into a lilac flame when reacted with water. The reaction is highly exothermic such that the hydrogen gas produced ignites. It burns with a lilac flame due to the presence of potassium vapor. Reactions with chlorine. Alkali metals react with chlorine to form their corresponding metal chlorides. Reactivity increases down the group. When hot sodium metal is lowered into a chlorine jar, it bursts into a yellow flame, forming white fumes of sodium chloride. Sodium reacts with chlorine to form sodium chloride. Lithium reacts with chlorine to form lithium chloride. Potassium reacts with chlorine to form potassium chloride. The equations for the reactions are as shown on that slide. Uses of alkali metals and their compounds. Sodium is used in making sodium cyanide, which is used in extraction of gold. Lithium is used in the manufacture of high special strength glasses and ceramics. Lithium compounds are used in the manufacture of dry cells for use in mobile phones, laptops, stopwatches, and zero-emission electrical vehicles. Sodium vapor is used to produce the yellow glow in street lights. Sodium chloride is used as a food additive. Sodium hydroxide is used in the manufacture of soap. Sodium is used as a reducing agent in extraction of titanium from titanium 4-ox chloride. A molten mixture of sodium and potassium is used as a coolant in nuclear reactors. Now that marks the end of our long lesson. I hope you are able to capture at least something. Welcome to our next lesson in the next class. Thank you and be blessed.